Okay, hi everyone. So this week we are going to be talking about logic. So this is our last set of modules, and we're going to switch from variable-based models and start talking about logic. So let's start with a question. So let's start with this question. If x1 plus x2 is equal to 10 and x1 minus x2 is equal to 4, what is x1? Okay. So think about this for a few seconds. So the way you would go about this is you'll probably use the thing that you've used in algebra and then basically cancel out x2's together, and you would have 2x1 equal to 14, divide 14 by 2, and you'll end up getting 7, right? Another way of looking at this problem is you can think of this as a factor graph. This is actually a factor graph, and we have these constraints. And one way of solving this is to go and do backtracking search and then actually try to figure out the satisfying assignment there. But the problem there is that might not be the most efficient way of doing it, and kind of like the trick that you've learned in algebra is probably a more efficient way of dealing with this question. So that is kind of like a motivation for why we are talking about logic. Could we do logical inferences in a way that makes our lives much easier and allow us to talk about expressions much more concisely and allow us to move around symbols and come up with decisions, come up with solutions based on these sort of logical inferences. So have this example in your mind throughout the lecture, because we are using similar type of ideas when we talk about logic and doing inference in logic. So if you remember our course plan, right, we started with machine learning, and then we talked about, in general, reflex-based models, where we have a low level of intelligence, and we started adding to these levels of intelligence, thinking about state-based models, and then thinking about variable-based models. And finally, we are at logic, when we are talking about a higher level of intelligence and expressivity when we think about AI systems. And just taking a step back and thinking about the paradigms that we've used in this class, we started thinking about learning and modeling and inference. So the idea was we have some sort of data. From that data, we're going to learn a model. We're going to learn this representation. And then we're going to be able to do inference on that model. So once we have a model, once we have an MDP, once we have a search problem, we can basically ask questions, and that's inference, right? We can basically ask questions and infer an answer, and that allows us to think about different types of inference algorithms. Okay. So examples of that is we talked about search problems. So when we have a search problem, like the objectives inference problems that we're thinking about was finding a minimum cost path. Or we were talking about MDPs. So in MDPs, for example, or games, we were thinking about maximum value policies. Or we looked at CSPs or Bayesian networks, where we were looking at basically what is the probability of some query conditioned on some sort of evidence. So these are some examples of inference questions, inference problems that we have looked at throughout the different lectures and modules that we have seen. So in modeling, so when we think about modeling paradigms, when we have state-based models, we thought about search problems, MDPs, and games, and we basically thought about these in terms of states, actions, and costs. Right, so those were kind of the main core elements that would come into our modeling when we were thinking about state-based models. And applications of that were things of the form of route finding or playing games. And then when we started thinking about variable-based models, we started defining this idea of variables and factors and constraints between them. And then we talked about CSPs, we talked about Bayesian networks, Markov networks, and applications of that were things that was easier to think about in terms of variables. So we talked about scheduling or tracking or medical diagnosis, where we have dependencies between these different variables. And that was in variable-based models. So in this week, what we want to do is we want to talk about logic-based models. And in logic-based models, similar to state-based models and variable-based models, we are going to define a few different types of logic that we are going to be using. So specifically, we're going to be talking about propositional logic and first-order logic. And we're going to think in terms of logical formulas and in manipulating these logical formulas and how we can infer new formulas from them. So specifically, how we think about inference rules. And what are some applications of logic where logic shows up in a variety of applications, starting from theorem proving, hardware and software verification, and also in general, like reasoning. It's a core element of reasoning in artificial intelligence. So historically, if you think about logic, kind of like back, like old AI was very highly dependent on logic. So logic was dominant in AI like before 1990s. So the same sort of excitement, the same sort of hype that is around deep learning today, that same sort of hype was around logic before 1990s. And that was kind of like the core of AI. People were thinking logic is going to give us really understanding of artificial intelligence and developing artificial intelligence that could really achieve things that humans can. But that didn't really pan out. And the reason it didn't pan out was logic had a few problems. So the first problem was logic was deterministic, right? And it couldn't really handle uncertainty. And that gave rise to things of the form of probabilistic inference and in general understanding probabilities and adding uncertainty on top of logic, or developing models that can capture uncertainty beyond logic. The second problem with logic-based models were they were very rule-based, and they wouldn't allow like fine-tuning based on data. So because of that, they were very brittle. So if I have new data that comes in and tells me something else, then that rule-based model is not going to be able to capture that, and it's really hard to incorporate information coming from new data. And again, that gives rise to machine learning and then this idea of data-driven models and looking at data and being able to learn new models and being able to do inference from that perspective. Okay. But so these are kind of like the problem 1 and 2 are weaknesses of logic, but in general, logic has some sort of strength that some of our models today, like some of the state-of-the-art models today, don't really have that. And I think there is really an opportunity here to use ideas from logic in some of the more modern machine learning systems or some of the more modern AI systems. And the strength of logic is expressivity. So we're going to be talking about this throughout this week in general, but the nice thing that logic gives us is it provides a compact way of expressing models, expressing representations that we wouldn't normally be able to get. So this compact representation can be really powerful because we could manipulate that compact representation, and that could allow us to move in to be able to infer new ideas, infer new rules, and so on. And in general, that expressivity is a big strength of logic and the reason that it is still around and there's still excitement around using it. All right, so let me motivate logic with an example. So we've looked at this example. I think Percy showed this example during the first lecture, where our goal is we want to have a smart personal assistant. So let's say we're sitting on the beach and this is after the class and we're on vacation and after COVID, and we're sitting on the beach and we have a personal assistant. And what we want to do is we want to ask our personal assistant, maybe it's Siri, or maybe it is something fancier than Siri. And we want to ask our personal assistant a set of questions, or maybe we want to tell it some information. Maybe we want to inform it about something or ask questions from it. Okay, so, and let's say we use natural language. So let's start with natural language as a medium for talking to this personal assistant. Okay, so let's look at an example here. So this was the system. So let's say that this is my system, and I tell my system, all students like CS221. Okay, so I'm telling it some information, and then my personal assistant says I learned something. Okay, then I can say Bob does not like CS221. Okay, and then it would be like I learned something. And now based on this knowledge that it has, like let's call that knowledge base. So based on this knowledge base that it has, I can ask this personal assistant questions. I can ask, is Bob student? What should it answer? So if it actually does inference, right, it should answer no, right? Like if it has a set of formulas and based on those it can infer and it can reason, then it should actually be able to answer that question. Underneath here, there are a bunch of formulas and there are a bunch of inference rules. We are going to be talking about that, but we could take a look at that and see what are the formulas that it has access to and what are the things that it is inferring. It is inferring that Bob is not a student here based on the things that I've told it. But this is kind of, this is an environment that we're going to be talking about throughout the lectures and other modules this week. All right, so let's go back here, okay? So in general, when we think about having this personal assistant where we are using natural language or where we are using logic, the idea is it should be able to digest heterogeneous information, and it should also be able to reason deeply about that information, right? It can't have just shallow knowledge of that information. It should be able to do inference. It should be able to connect these different pieces of information and make logical statements based on them, makes logical moves based on them. Okay. So why should we use natural language? That's a good question. Why natural language or like anything else? Okay. So natural language is kind of nice. We all like speak in natural language. I'm talking to you guys in natural language. It's a very nice medium to use when we talk to personal assistants or when we want to basically express what we would like to say. So it's a very rich medium for expressing what we want. And because it is rich, we can say things like, I don't know, a dime is better than a nickel. And we can say things like a nickel is better than a penny. And based on that, we could be able to make expressions. We could make logical statements based on that and say, therefore, a dime is better than a penny, which makes sense. But the problem with natural language is it's also a little bit slippery. Like I can start with something that says a penny is better than nothing. That's okay. And then I might have another statement that just says nothing is better than world peace, and that's perfectly fine. And putting these two together, I can come up with a logical, like, kind of a statement based on what I've seen, that a penny is better than world peace, which sounds a little bit weird and not correct and not the thing that I actually wanted. Okay. So even though natural language is pretty rich, when we are thinking about logical statements and making logical inference here and following like inference rules, it feels like natural language is a little bit slippery, and we might want to have access to some other type of language. So this language, like when we talk about language, it doesn't need to be natural language, right? Language is just a mechanism for expressing things. It's just a way of expressing, okay? So natural language is an example of a language that allows us to express things. It's kind of informal. We also have programming languages those are kind of formal, like we have like Python or C++. In addition to these, we can have logical languages. And the nice thing about logical languages is that they're formal, and we can think about the relationship between them and formal connections between them. But the other nice thing about logical languages is they're actually closer to natural language than, let's say, programming languages, because they're declarative. So there is like actually a connection between natural language and logical languages. In one of the later modules, we're actually going to talk about how we can write expressions in first order logic if we have a natural language statement. So in this lecture this week, we are going to be talking about two types of logical languages: propositional logic and first order logic. All right, so what is the goal of a logical language? So the goal here is to be able to represent knowledge, right? We want to be able to represent knowledge about the world, but that is not the only goal. In addition to that, you want to be able to reason about that knowledge, right? It's not just about representing it, it's about how we can make logical statements, and how we can run inference rules, and how we can make new statements and reason about them. So an example is, if I tell you guys it's raining and it is wet, you should be able to reason about that, and you should be able to figure out that, well, it is raining then, right? Like, you're telling me raining and wet, so it is definitely, like, both of those statements are true, and you should be able to reason about that. And that is the goal of a logical language. And when we think about logic, we have kind of three main ingredients for logic. I'm going to go into these details a little bit more in our first module, but let me just give you a quick overview. So we're going to have syntax, and syntax basically tells us, like, are the symbols of that language. So basically it defines a set of valid formulas. So syntax here, for example, in a logical formula, in propositional logic, syntax could be rain and wet. Okay, so when I write rain and wet here, this and in the syntax land doesn't have any meanings. It's just a symbol. It's just like this shape. Okay, and rain and wet, they don't have any meanings. They're just symbols. Okay, so when you're talking about syntax, you're really talking about the symbols that are building blocks of language. But symbols are alone, like syntax alone, is not going to be able to define a language. In addition to syntax, what we need is semantics. We actually need to give meaning to the syntax. So for each one of these formulas, we need to be able to specify a meaning, or we specify and meaning has a very, very precise meaning to it. So meaning corresponds to an assignment, a configuration of the world, like a setting in the world that corresponds to that formula, that corresponds to that syntactical formula. So for example, in the case of rain and wet, it actually corresponds to a specific meaning where rain takes value 1 and wet takes value 1. And this is like a specific model, a specific world where we live in. And in this world, rain and wet has this particular meaning. Okay? So the main ingredients of logic are, first off, syntax and semantics. And once we have syntax and semantics, then we can talk about inference rules. We can actually talk about what can we infer now that we have a set of formulas, or we have a set of knowledge about the world. So given that we have a formula F, could we infer, could we derive a new formula G? Could we figure out like if G is true or not based on F? For example, like if you tell me rain and wet as a formula, from that, I can derive rain is also true, right? Because it's got to be rain and wet. So from that, I should be able to derive rain. And then that's what we are going to spend quite a bit of time this week. Like, what are the inference rules that we can play around with, and how do they apply to different types of logic? Okay, so 3 ingredients: syntax, semantics, and inference rules. All right, so let me just make a bigger point for this difference between syntax and semantics, because the difference might be a little subtle. So again, if you think about syntax is talking about the valid expressions that are in your language. It's basically talking about the symbols, right? The things that are valid to say in the symbols that are valid to write in this language. Semantics is about what the expressions means. So let me give you an example here. So let's say we are looking at 2 plus 3 versus 3 plus 2. Okay, 2 plus 3 and 3 plus 2 have different syntax. They're not the same. They don't look the same. If I have no idea what 2 means or plus means or 3 means, right? 2 plus 3 has nothing to do with 3 plus 2. They have 2 very different syntax, but they have the same semantics, right? If I know what plus means and what 2 means and what 3 means, and if I know what 2 plus 3 is 5 and 3 plus 2 is 5, then they have the same meaning. They have the same semantics. So different syntax, but similar, the same semantics. On the other hand, we can have settings where we have the same syntax, things look the same, but they have different meanings. For example, you can look at 3/2 in Python 2.7 versus Python 3. And in that case, it's like it looks the same, 3 looks the same, the divide looks the same, 2 looks the same. So syntactically, these two are exactly the same thing, but semantically, they have different meanings. They actually correspond to different values, right? When you're doing this in Python 2.7 or Python 3, okay? So again, we have 2 expressions that have the same syntax in this case, but they have different meanings and different semantics. So syntax and semantics are 2 different things. Both of them are needed to define a logical language. And I want to kind of like end with this view and this diagram that I'm going to come back to and explain it in a bit more detail in kind of future modules. So the idea is we have 2 worlds here. We have on the left, we have syntax land, and on the right, we have semantics land. Okay, so in syntax land, we have formulas. So I'm going to use these rectangles to kind of like represent formulas. These are different formulas that I can write, like rain and wet. And each one of these formulas have a meaning in the semantics land. Okay, so each formula has a meaning in the semantics land, and that's called models here. And what our goal is throughout the lecture is to come up with inference, like first define syntax and semantics for different types of logics, and then after that, come up with inference rules that allow us to manipulate these formulas, these compact formulas that are kind of like nice and expressive, and manipulate them and come up with new formulas, infer new formulas that have meanings that are also entailing the meanings of our current formulas. So more on this later. If this is confusing, I will talk about this in more details in a few modules. Just to give you a quick overview of different types of logics we will be talking about, there are different types of logics, and in this order, they're kind of like increasing in the order of increasing of expressivity. So, and in this week, we are going to be talking about the bolded ones. So we will be talking about propositional logic, and specifically propositional logic, a subset of it that only has these things that are called horn clauses. So we'll talk about what those are. And we will also talk about first order logic. So first order logic only with horn clauses and just generally first order logic. There are other types of logic that we're not discussing in this class, second order logic, temporal logic, and they're actually quite useful in a variety of fields, in programming languages and robotics and formal methods. And yeah, like if you're interested in any of these, we can chat about it offline. One other point I want to make is as we increase like the level of expressivity of logic here, like as you go down in this list, like expressivity of these logics is going higher and higher. But the thing that you're losing on is computational efficiency. So if you want to run inference rules, it's going to become much more difficult if you're running it on first order logic as opposed to propositional logic. So there is a trade-off between computational efficiency and expressivity of that logical language. All right, so with that, this is the roadmap for this week's lectures. So we're going to start with kind of like modeling. And by modeling here, what I mean is defining the syntax and semantics of logic. So we're going to talk about propositional logic and the syntax of that. Then we are going to talk about the semantics of propositional logic. At that point, we're going to be switching to inference and discussing inference rules. In general, we're going to be talking about two main inference rules. Modus ponens is one, and the other one is resolution. So we're going to talk about under propositional logic, how do we do modus ponens? How do we do resolution? At that point, we're going to switch back to a higher level of expressivity in terms of our models. We're going to talk about first order logic after that. Again, syntax and semantics of first order logic. And then after that, we're going to talk about modus ponens, again, an inference rule for first order logic. And we have an optional module at the end, which is about resolution for first order logic. This gets a little bit hairy, but if you're interested, you can kind of look at this and how resolution gets applied to first order logic. And then we're not talking about learning during this week. In general, learning more recently has been applied to kind of logical formulas, specifically in the area of formal methods. People have been thinking about learning logical formulas from data, from demonstrations, but that's outside the scope of this class, so we will not be talking about that.